What if the secret of life was hidden not in biology, but in physics? In 1943, one man went looking. This is what is life. Dublin, February 1943. In a packed hall at Trinity College, a man who helped invent quantum mechanics rises to speak. But he has not come to talk about atoms. He has come to ask a biologist's question, one so simple a child might ask it, and so deep that no one had truly answered it. What is life? His name was Erwin Schrodinger. He was already one of the most celebrated physicists alive. His equation sat at the very heart of the new physics. But he had grown restless with a quiet assumption, the idea that living things might somehow stand outside the laws that govern everything else. He set out to show that they do not. Here is the puzzle that haunted him. At the smallest scale, physics is chaos. Atoms jitter and collide at random, never still. The order we see in the world, the sharpness of a law, the steady pressure of a gas, is only an average, a truce struck across countless trillions of restless particles. Schrodinger called it the root n rule. The precision of any physical law improves only with the square root of the number of atoms involved. Across a million particles, the noise still whispers at 1 part in 1,000. Physics, in other words, only becomes lawful in the crowd, but heredity breaks the rule. The instructions that shape a living creature are copied faithfully, generation after generation, and they are carried by a structure of only a few thousand atoms. Far too few for the safety of the crowd. So how does life stay so reliably, so stubbornly itself? Schrodinger's answer was a leap no biologist had dared. The gene, he argued, could not be a fragile statistical average. It had to be a single, stable molecule, its order built into its very structure, not borrowed from large numbers. A thing that is orderly because of what it is. And if the gene is a molecule, then quantum mechanics rules it. A molecule rests in stable configurations, separated by walls of energy. To change one, you need a discrete jump, a quantum leap. This, Schrodinger realized, is exactly what a mutation is. Not a gradual smear, but a sudden all-or-nothing switch between stable states. Heredity that is faithful, yet free to change in an instant. Then came the prophecy. What kind of structure could be as stable as a crystal, yet rich enough to hold the entire plan of a living thing? An ordinary crystal, salt or quartz, repeats the same dull pattern forever. It is stable, but it says nothing. Schrodinger imagined instead an aperiodic crystal, orderly and durable, but never repeating, its units arranged in an endlessly varied sequence. In that non-repeating order, he saw a code, a miniature script, written in the very arrangement of atoms, capable of holding the instructions for an entire organism in a vanishingly small space. He was describing the essence of DNA, nearly a decade before anyone glimpsed its double helix. But Schrodinger pressed further, towards something deeper than chemistry. Ordinary physics, he said, makes order out of disorder, the tidy average that rises from a random crowd. Life does the opposite. Life makes order from order, passing a structured pattern forward, faithfully, from one generation to the next. Everything in the universe drifts toward disorder. Entropy always rises. A living thing seems to defy this, holding its exquisite order against the tide. How? Not by breaking the law, but by feeding. An organism stays alive, Schrodinger wrote, by drinking order from its surroundings. It feeds on negative entropy, taking in order and exporting the chaos. In a final, more personal coda, he turned from the cell to the mind, to consciousness and free will, drawing on the Vedanta philosophy he loved. For Schrodinger, the question of life was never separate from the largest questions a human being can ask. The little book, barely 90 pages, landed like a seed. A young James Watson read it, so did Francis Crick. Both later said it set them hunting for the molecular secret of the gene. The aperiodic crystal they were chasing turned out to be the double helix. And here is the lesson that outlasts the science. Schrodinger ran no experiments. He kept no laboratory. He simply carried a physicist's questions into a field that was not his own, and refused to accept that life could be an exception. The breakthrough came from the crossing. That is the thread that runs through every book in this series. The most original ideas tend to appear at the borders, where one discipline dissolves into another. What is life is where we begin, because it asks the oldest question with the newest tools. Read it, and then go find your own border to cross.